Okay, let's talk about assignment 22 today. Assignment 22, and that's all about inverse trig graphs. Okay, but first, before we get into the details of inverse trig graphs, I kind of want to say, so this word inverse, does every function have an inverse? I think it's a great place to start this conversation. Y equals sine x. Okay. Sine x. We know the domain of sine x is negative infinity to infinity. This graph keeps going forever. This is pi, 2 pi, minus pi, etc. Okay. I know the period for sine is 2 pi, but I want to ask this question. Does this graph have an inverse? Or said a different way, does this graph pass the horizontal line test? The answer is no. We failed the horizontal line test here. So what happened before when we failed the horizontal line test? That's right. When we had parabola, we had to restrict the domain of the parabola to just that amount where we could get all the positive and negative outputs for sine, but also still pass the horizontal line test. So, for example, what if I restricted the domain to 0 to pi? Would that pass the horizontal line test? No. So, yeah, 0 to pi, not going to work. Pi to pi over 2, not going to work. Fails the horizontal line test. Remember, I want to get not only all these positive y values here, these positive sine values, but I also need to get all the representative negative sine values. And so what was decided without anyone asking us is that we would go from here to here. Okay? This part of sine from negative pi over 2 to pi over 2. This is the part of sine we're going to work with. Okay, well, let's see what we know. If we're only working with this would be negative pi over 2, negative 1. This will be 0, 0. And this will be pi over 2, 1. Oh, I feel like we've got a reference graph going on here. Okay, so we've got this reference graph now. This is our sine reference graph for inverse sine. So tell me, how is it that we make an inverse? Well, with the exception of word problems, we talked about this last semester and said we're always going to do the same thing. So what is it that that we ought to be doing here? Well, we need to switch these ordered pairs. So my inverse will have the point 1 pi over 2, we'll have the point 0, 0, and we'll have the point negative 1, negative pi over 2. Yeah? These green points are going to be the points on our inverse graph. And notice here, these are endpoints. The function stops, starts here, ends here, full stop. If you do this, yeah, Justin's going to mark that wrong because this graph can't go further, fails the horizontal line test. Okay, so let's plot these points. Oh, and notice here that on regular trig graph, that's an angle. And if we're talking about sine, we have an upness as an output. But on our inverse trig graph, y equals sine inverse of x, in this situation, the input is the upness and the output is the theta. Huh, okay. So we've got 1 pi over 2, we've got 0, 0, and we've got negative 1, negative pi over 2. Now, I've certainly graphed these points in a way as to suggest um, that this number and this number are the same, because they kind of look like the same. I'm not yet, but no. 1 does not equal pi over 2. Pi over 2 is 1.57 something. That's not the same as 1. And I think that's kind of important to bring up, both because it often leads to students thinking that this is the graph, and that's not the graph. Remember, a graph of a function and that function's inverse should reflect across the line y equals x. So when I think about drawing the inverse, I'm thinking about this, and this, and this. Go down, don't give up. And I would have something like that. So that, and then that. That's my inverse sine graph. This is sine. Concave up to concave down. Inverse sine. Concave down to concave up. Yeah, two different things going on here, right? These are not the same. They don't have the same points. This is 1 pi over 2. This is negative 1, negative pi over 2. All right, they both share 0, 0. But that's it. I could graph them on one graph, and they should reflect across the line y equals x. Yeah, that's it. Don't continue this. Oh my goodness. There are some people who want to do this. It fills me with anger and quiet tears. There are no vertical asymptotes on inverse sine or inverse cosine or even inverse tangent. Now, I will say that the slopes at these points, the slopes are approaching infinity, but these are not graphs that go down and up forever. This is a hard stop. This is a hard start. There is no more besides this, or else this will fail the horizontal line test. And no, I mean, if we continued this inverse trig graph, the inverse trig graph looks like that. And that fails the vertical line test. So then inverse sine can't be a function anymore. So no, stop it. Try, don't make all those thoughts. Instead, we're just going to flip these points from our restricted sine graph to get our reference points for inverse sine. This is my reference graph. And it's true, in this situation, I'm going to be doing transformations when I see these inverse trig functions. So if I'm given y equals 2, let's do that one, sine inverse of x minus 1 plus 2, pi over 2, I feel like I'm really well set up to do transformations. I have to know this shape. I also have to know what are the reference points. So sine inverse x, reference points, what were they? They were negative 1, negative pi over 2, 0, 0, 1, pi over 2. There were no vertical asymptotes, there were no horizontal asymptotes, so really all I have to do is apply these two transformations to these ordered pairs. So what do we know? Well, this is inside our inverse trig function. Does that affect x's or y's? Yes, x's, I agree. And will I subtract 1 from all the x's? No, inside is opposite land. We're going to be adding 1 to all of the x's. And that will cause our inverse sine graph to move to the right 1. We also have this transformation. That's outside the function, so that affects my y values. Adding pi over 2 to the y values is going to shift my graph up pi over 2. So what points am I going to have? Well, negative 1 plus 1 is 0. Pi over 2 plus negative pi over 2 is 0. We've got 1 pi over 2 and 2 pi. These are our 3 points. Okay, so this is 0, 0. This is 1 pi over 2. and this is 2 and pi. Now, there's a lot of ways we could connect these dots. The most common way I see students do it in this section is they draw a straight line. Very sad. Okay. Next, I see students doing this. Yeah, also sad. With our inverse sine graph, correct graph is that. So, I'm now going to share with you something that was shared with me many years ago by a fabulously observant student. The observant student said, Mr. Kukla, I was always getting confused whether I should go concave down to concave up or concave up to concave down. And what they're saying is, I was mixing these two up, the red one and the green one. And so what I finally... Yeah, I'm sorry, I have to walk it back. Because I'm actually listening to that student's voice in my head, and they said, they said, in fact, that was the good one, and that this was the bad one. And the way they knew that was because inverse trig, inverse sine, inverse cosine are always concave up as we head to that maximum, and concave down as we head to our minimum. Okay? So, yeah, that's the correct shape. That's the correct shape between those 3 points. And while I can put those 3 points on a straight line, no. Concave up, smiley face, as I head to the maximum point. Okay, so there's my graph. Don't forget, we want the points labeled on the graph. And this one, yes, there's that point there. Okay. So, one more. Let's do one. Remember, always concave up. So let's imagine we had this situation. Yeah. Let's imagine that we had a negative sine inverse of x. And so instead of this shape, which is sine inverse of x, we're multiplying all the y's by negative. Now we have this shape. Yeah? And look, as we go to the high point, my graph is concave up. So that may well be worth writing down. As we head to the high point, to the maximum, we want to be concave up. Okay, so concave up as I head to the high point, and concave up as I head to the high point. Good. Okay, so you were going to do one more. Let's make it a little more complicated. How about y equals negative 3 sine inverse of 2x plus 5 plus pi over 2. Yeah, a word. See that? There are some students who want to say that this means 1 over sine x. And so then they say, isn't that cosecant? And the answer is no, not at all. But Mr. Kukla, isn't this the exponential power raised to the negative 1 power? Isn't that what I've been doing since algebra 2? Well, if that were raised to the negative 1 power, I would completely agree with you that this would be our relationship, except that's not raised to the negative 1 power. That's inverse sine, right? When we had sine x equal to 1/2, we took the inverse sine of each side, not the reciprocal of sine. And I'll show you why in just a second. Inverse sine and sine cancel each other out, leaving me x equals sine inverse of 1/2. Now, let's imagine we're here, and we're under the misapprehension that this is 1 over sine x times sine x, and on the other side, we have 1/2. Well, look, sine divided by sine is 1, and 1 does not equal 1/2. So no, this is not the reciprocal of sine. That does not work. Okay? This is inverse sine. And so what I'm going to do to graph this is to say, okay, I know my reference points for inverse sine. We're at -1, negative pi over 2, 0, 0, and 1 pi over 2. And I'm going to apply these transformations. In fact, you should go apply these transformations. Pause the video and come back when you're done, and we'll take a look at this. Hey, welcome back. So I see two transformations with x's and two transformations with y's. I have to do PEMDAS for the y transformations, so I'm multiplying by -3. And for x transformations, I'm doing SADMEP, so I'm going to subtract 5 from all the x's. This is going to bring me to -6. Negative times negative is positive, 3 pi over 2. I've got -5, 0, and I've got -4, -3 pi over 2. Great. But I'm not quite done yet. Yeah, I still have two more transformations to apply. I have to divide all the x's by 2, and I have to add pi over 2 to all the y's. Okay, so I'm going to end up with -3, 4 pi over 2, which is 2 pi, -5 halves, pi over 2, and -2. -3 pi over 2 plus 1 pi over 2 is -2 pi over 2, 1 negative pi. All right, so think about the shape. This is inverse sine, so let's think about that shape. Ooh, and let's think about that. What did that do? Well, that flipped my graph. So the high y value, -3, 2 pi. Then our inflection point, -5 halves, pi over 2. And here we've got -2, pi. And I would almost beg you to look at this. Because sometimes what happens is people take this point and put it over here, and this point and put it over here, because they see that positive 2 pi, and so they think, oh yeah, 2 pi is that way, and -pi is over there. No. Yeah, please look at these reference points when you think about what's got going on here. The highest y value is at this x value. This is the lowest y value at this x value. So please make sure they match up, okay? All right, well, there's the graph, and that's it. That's the whole graph. If you put an arrow on that, yeah, marking it wrong. So don't put an arrow on it, yeah? That would be cool. All right, so there's inverse sine, and we're back in happy transformation land, and so that's fabulous. What about y equals cosine x? Does this pass the horizontal line test? No, it doesn't, does it? And we know that our we know that the reference graph here looks like that and that. Okay, so there's two periods of cosine. There's 2 pi, there's pi, -pi, -2 pi is here. And that is -pi there. Okay, and this goes on forever. Yeah, fails the horizontal line test. So again, we want to restrict the domain of cosine so that cosine can pass the horizontal line test. Can we use the restriction we had for inverse sine? Does that work? Is that our magic boundary that will help us every time? Yeah, no, because if I go from -pi over 2 to pi over 2, I'm definitely failing the horizontal line test. Well, that kind of sucks. Well, what if I want to get all the positives and all the negatives with passing the horizontal line test. And the people who were alive at that time thought that this would be our restriction. So we're going to restrict from 0 to pi. Okay? Okay, so what points do we have here? Well, this would be 0, 1. This would be pi over 2, 0. And this would be pi, negative 1. So if these are the points on cosine, what can you tell me about inverse cosine? Their points would be 1, 1, 0, 0, pi over 2, and negative 1, pi. These are the points for inverse cosine. Okay, so let's graph inverse cosine. Inverse cosine, we're at 1, 0. We're at 0, pi over 2. And here, negative 1, pi. If you want, of course, you can draw in the axes to see your graph. And again, this is the whole graph. There's not more to this graph. No more, no more, no more. This is it. You put an arrow on the end, yeah, we're marking it wrong. Okay? And this is going to be another situation where, look, as we head to the high point, the function is concave up. We're not concave down headed to the high point. We're not linear headed to the high point. We're concave up headed to the high point. And for inverse sine and inverse cosine, we're always going to be concave up as we head to the high point. Yeah? Okay, so we've got a reference graph. Let's then graph some inverse cosine stuff. Y equals 2 cosine inverse x plus 3 minus pi over 3. Okay? Okay. So start with those reference points. 1, 0, 0 pi over 2, negative 1 pi. And I see a bunch of transformations here. I only see one x transformation. This one here that's going to shift my graph left 3, because I'm going to subtract 3 from all those x values. And what about these y's? Well, I've got 2 y transformations. Do I multiply by 2 and then subtract pi over 3, or do I subtract pi over 3 and then multiply by 2? Well, we know that y transformations, transformations outside of the function, we use PEMDAS. And PEMDAS says multiplying has to come before subtracting. So I'm going to multiply by 2, by 2, by 2. And so what are my new points? My intermediate points. I've got negative 2, 0. Negative 3 pi, and positive 3. That seems something really wrong. Am I subtracting? There we go. Negative 4. And multiplying here, so I got 2 pi. Okay. Don't forget we've got one more round of y transformations to do. And that's going to ask us to subtract pi over 3. From each of the y values in our ordered pair. Three pi over 3 minus 1 pi over 3 is 2 pi over 3. This is 6 pi over 3 minus 1 pi over 3 is 5 pi over 3. All right. So let's graph. We've got negative 2 negative pi over 3. We have negative 3 positive 2 pi over 3. And we've got negative 4 5 pi over 3. You know, make sure the point that has the biggest y value is the highest point on the graph. Is this our graph? No, we're not concave up going to the high point. So please, concave up going to the high point, concave down going to the low point. That's our graph. That's our graph. with these three ordered pairs. Okay. How about this one? Can you graph this one for me? Y equals -2 cosine inverse 1/2 x plus 1. All right. Show me what you got. Pause the video, give it a try. I look forward to checking the answer and seeing how well you did. Yes, you do need to use those reference points again. So what reference points are we talking about? What are the reference points for inverse cosine? Well, I've got 1, 0, 0 pi over 2, and I have -1 pi. Remember, the normal inverse cosine shape looks like that. So I see I'm moving left 1, and then horizontally stretching this. Then I see I'm multiplying all the y's by 2, so I'm stretching vertically, but I'm also flipping upside down. And somehow, even though I know all of those things are happening, I really don't see the graph yet. I'm going to apply these transformations. So we've got 1, 1 transformation. Multiply the y's by -3. And I see 2 x transformations here. So let's say sad map on the inside, which means I'm going to subtract 1 from all the x's. That gives me these transitional points, 0, 0, -1, -3 pi over 2, -2, -3 pi. Okay, and now, do I have anything else? Yes, I've done 2 transformations, but there's 3. I still need to do that, which means dividing all the x's by 1/2, or multiplying the x's by 2. And so the final points, the points that I'm going to graph, are going to be 0, 0, -2, -3 pi over 2, -4, positive, -3 pi. Okay. So what does this graph look like? Well, that reflects my inverse cosine graph that normally looks like this. That's inverse cosine. This multiplies all the y's by -1, and that's going to cause this to reflect. So now I'm going to have this graph. Looks a lot like inverse sine. And what I'm saying is this point that's furthest to the left with this most negative y value goes there. Now I've got -2, -3 pi over 2, and finally 0, 0. Now, one of the things that I notice that students do when they need to graph this, even if they know what the shape is supposed to look like, and even if they know it with that negative in front, I still get students graphing this a different way. People put 0, 0 here. They put this is usually the same, and then this one becomes -4, -3 pi. And, there's precisely 2 problems with that. The first is that -3 pi should be below 0. This is a negative number. This is 0. This has to be, both of these have to be below the y value here. And that's not true in this red understanding of what's going on. The other thing that happens is, here the x value is 0, and then we have an x equals -2. Oh no, and an x equals -4? How if I move this way, are my values going from 0 to -2 to -4? Mrs. Rowan said in the 7th grade that negative numbers go that way, to the left of 0. So I want -4 to be to the left of -2, to the left of 0. And that's not what I get in this situation. Yeah, so think about those transformations. And that's the whole graph, not that erroneous red bit. All right, there's my transformed inverse cosine. Next, inverse tangent. Well, the cool thing about inverse tangent I think, inverse tangent. So let's graph y equals tan x. Okay, there's one period. This is negative pi over 2. This is pi over 2. And we have that inflection point 0, 0. That's y equals tangent x. All right, oops. Y equals tangent x. Now I'm looking for the inverse. So how do I consider that? Well, this pair flips, still looks like 0, 0. But remember, these vertical asymptotes have a name in math, and they're called x equals. X equals a number is this vertical line. So what must exist, not on tangent, but on inverse tangent? If I flip the x's and y's, I still have the ordered pair 0, 0. But if I flip the x's and y's, what do I have now? Y equals negative pi over 2. Y equals positive pi over 2. X equals a number is a vertical. Y equals a number? Yeah, y equals a number. These are horizontal asymptotes. So we've got negative pi over 2, we've got positive pi over 2. We have our characteristic shape. We have 0, 0. Okay, so there's your reference graph for tangent. We don't have any domain restrictions like we did with sine and cosine, though this one actually comes with sort of built-in restrictions. You know, all the angles, all the outputs. Remember, this is a tangent value going in, and on the out we have an angle. It's the angle that has that tangent value. Okay, so what I'm thinking about here is these vertical asymptotes on tangent become horizontal asymptotes on inverse tangent. That's good. As far as I got with that. So, you know, if I'm talking about doing transformations of this, this is really supposed to be very easy. We've got one ordered pair, and we have two horizontal asymptotes. So when I look at something like this, when I look at y equals 2 tangent inverse of x minus 3, I think, okay, I've got one ordered pair, and I've got y equals negative pi over 2, and y equals pi over 2. These are my reference point and my reference horizontal asymptotes. So let's, let's apply transformations. This gets applied to all the y values. Times 2, times 2, times 2. This gets applied to all the x values. I add 3. Oh, those aren't x values. So I guess that's the only place I carry out an x transformation. That's the only place I carry out an x transformation on the inverse tangent graph. You know, if we were doing quarter points again, you would see that better. But really, I think this is fine. Okay, so our new points, 3, 0. We have y equals negative pi for a horizontal asymptote, and y equals pi for a horizontal asymptote. This is y equals pi. This is y equals negative pi. Okay, we have a positive inverse tangent. And I know my graph looks logistic. But if this were logistic, this would be pi. I'm sorry, 0, and that would be pi. This bottom one for logistic is always at 0. Okay, anything else we need to do? Yes, please label the inflection point, 3, 0. And label the asymptotes. We've got asymptote at negative pi. We also have an asymptote at pi. Look, I have done And there's my inverse tangent graph. That's it. That's all there is. There's nothing more. It's not scarier than that. Yes, there's only one place to apply x transformations to, but there are 3 places to apply y transformations. So please make sure you make a note of that. Now, once you're done making that note, will you please graph this one? Okay. You know there's only one reference point on inverse tangent, but you also know that, you also know that y equals negative pi over 2 and y equals pi over 2 are things that need transformations, y transformations applied to them. So, what did you do first? What? Well, go pause the video, go do it, and come back. Hey everybody. So, I see 2x transformations. I do sad math, which means I subtract 5. There's nowhere else to do an x transformation. So now the y transformations. Do I add or multiply? I multiply first. Times 1/2, times 1/2, times 1/2. So now I've got negative 5, 0. 1/2 times negative pi over 4 is going to be y equals negative pi over 4. And here 1/2 times pi over 2 is going to be pi over 4. So I have these 2 horizontal asymptotes, and I have this inflection point. Whoa, wait a minute, Mr. Koopa. You're not done. Yeah, I agree. Good catch. We need to divide all the x's by 2. Oh, there are no more x's, so that's the only thing I divide by 2. But we're also going to add pi over 3 to each of the y values. Okay. So our final points, the ones that we're going to graph, we've got negative 5 halves. Subtract out minus pi over 3. And we have y equals, so this is negative 3 pi over 4, negative 3 pi over 12, plus 4 pi over 12. I add those, I get 1 pi, and double the denominator, 1 pi over 24. I'm kind of weary about that one. I'm tempted to go back and try it again. Minus 3 over 12 plus 4 over 12 is 1 pi over 12. And then what about here? Well, again, I'm going to have 3 pi over 12 plus 4 pi over 12 when I make the denominator. Okay, so 3 plus 4 is 7 pi over 12. 4. Oh. Yeah, that's it. So, what's our graph going to look like? Well, we've got a horizontal asymptotes. Oh, that's, sorry, it's not an order there, it's a horizontal asymptote. That was why I was confused. So this is pi over 12. This is y equals 7 pi over 12. And we have our shape, as well as our inflection point. Negative 5 halves, negative 5. Okay. There was something else I wanted to look at with this one. What was it? Yeah, when I think about the original function, my original function was shifted up pi over 3. So I'm no longer at negative pi over 2. I've shifted up pi over 3. Negative 2 plus pi over 3. And that's going to be minus 3 6 plus 2 6 is minus 1 6. Why is this? Oh, because there was that dividing by 2 that had to happen first from the original function. Yeah, so I like these. Great. What would cause my graph to look like this? Everything's the same except the shape. What function is graphed in purple? Oh, this purple graph is y equals, that's the one we did, 2x plus 5. I believe that's the one we did. 1/2 tangent inverse 2x plus 5 plus pi over 3. Okay, so what has to happen to this function to make this purple graph? And the answer is pretty easy. We just multiply that leading term by a negative. So if I see a negative inverse tangent, we're going to have this shape. If we have positive inverse tangent, we're going to have this shape. Okie doke. You know, if we were in class together, I might give you a little quiz now, if time permitted. So why don't we give that a try? I'm going to have 3 functions here. And we can call it a video 1. Y equals 3 sine inverse x plus 1 minus pi over 2. Okay? Oops. Over 2. So, please graph this. Welcome back. Did you write down the reference points to start with? Yeah, those are going to have to be memorized, huh? Negative 1, negative pi over 2, 0, 0, 1, pi over 2. I've only got one x transformation to take care of, so I'm going to subtract 1 from all of my x's. But I see 2 y transformations to do. I know the multiplying I'm doing multiplying is going to happen first. So we've got negative 2, negative 3 pi over 2, negative 1, 0, and 0, 3 pi over 2. Good. Almost, but not quite done. We still need to take care of this. So subtract pi over 2. And what do I get? Negative 2 minus 4 pi over 2. 4 pi over 2, that's negative 2 pi. Here I have negative 1, negative pi over 2. And here I have 0. 3 pi over 2 minus 1 pi over 2 is 2 pi over 2. Or just pi. Okay? So what can we say about the graph of this? Well, we know that this function starts here and ends here. It does not go on forever. This is it. The graph starts here and ends here. I know it's a positive inverse sine, so I'm drawing the shape for positive inverse sine. This will be negative 2, negative 2 pi. This will be negative 1, negative pi over 2. And this point here is 0 pi. And there's my graph. All right. Okay. How about inverse cosine? Y equals 1/2 cosine inverse 3x minus 1 plus pi over 3. Okay. Give this one a try. Come back when you're done. Hey everyone, welcome back. Did you start off with the correct reference points? 1, 0, 0 pi over 2, and negative 1 pi. Okay, and we're thinking about this graph. No negative out in front, so I don't have to worry about reflecting that. This is my graph. And I see a bunch of transformations. So which one do I do first? Well, I'm going to multiply all the y's by 1/2 and simultaneously add 1 to all the x's. So that brings me to 2, 0, 1, pi over 4, and 0, pi over 2. Okay, are we done? Of course not. We've got to divide all the x's by 3. And we need to add pi over 3 to all the y's. Okay, so where does that take us? we've got 2/3 over 3. Seems reasonable. Ooh, 1/3. 1/3. Pi over 4 plus 2 pi over 4 is 3 pi over 4. Are you sure that's not supposed to be pi over 3 like it is for these others? Yeah, it really is. So let's get rid of that. So I'm looking at pi over 4 plus pi over 3. So this needs 3 over 3 and 4 over 4. And 3 pi plus 4 pi is 7 pi. And we've got 12. And we've got 12. Okay. And don't forget we've got this one other point here, which is 0. And I'm adding pi over 3 to pi over 2. So pi over 2 plus pi over 3. Pi over 6 plus 2 pi over 6. And I get 5 pi over 6. Okay. So, can we make graph? 2/3. Y values are getting bigger. So here. Pi over 6. Pi over 12. Alright. I guess we still need to consider these x values. -2/3 pi over 3. This was 0. Multiply by half, still 0. Added pi over 3. Yeah, okay. Positive cosine, positive inverse cosine. It's like that. So 2/3 3. 1/3. 12. 0. 5 over 6. Okay. How about one last one? Inverse tangents equals inverse. I'm going to say 3 tangent inverse. X minus 3 minus pi over 4. Okay. So in this situation, what do? Well, the answer is I use my reference point and my 2 horizontal asymptotes. Okay. I'm supposed to add 3 to all the x's. Well, that's the only x right there. Okay. Not much going on there. 3, 0. But we've also got these two y transformations. And I know that multiplying comes before subtracting. So let's multiply all the y's by 3. So this is still going to stay 0. Except now we've got y equals negative pi, negative 2 pi over 2. And here we have y equals positive 3 pi over 2 times 3 is 3 pi over 2. There's pi here. Okay, so let's make a graph. This is y equals negative 3 pi over 2. Y equals 3 pi over 2. And halfway down, we've got the inflection point, 3, 0. And that's it. Pretty fast, I think. So just get yourself comfortable with these inverse trig graphs. And, we will be doing a little more graphing. But that's all the sort of new graphing of functions that we need to worry about. So congratulations. I say you've learned a lot about graphing this year, but there's still a little more to come. Great. I look forward to seeing what questions you have, either I or Mr. Paz, and we look forward to helping you get comfortable with this. But really, most of this stuff that we just did in this video, yeah, you need to memorize your reference graphs and your reference points and the shapes. Okay? All right.